There we go. So, guys, today we're starting in this unit. This is all of Chapter 7. We'll be learning a few techniques for integrating and some more advanced techniques. We'll be learning how to solve an initial value problem. So we'll be wrapping up this unit with me giving you a differential equation that measures a rate of change like population growth and then leveling out. It's called the logistics equation. And we'll have the skills by the end of this unit to be able to take that differential equation and solve it. Okay, it's called solving an initial value problem. It's where I give you an initial point, coordinate, and I give you a derivative and then you solve it. And that's actually what we do in ordinary differential equations. So, I mean, it's like, after you've taken Calc 3, you might take ordinary differential equations. We'll learn at least separation of variables. And they've put that into this course. It's not difficult. It totally relates to what we're doing. And I think it'll be a good connection. Is anybody taking is AP Bio this year? Anybody taking AP Bio? Okay, it's a good connection to AP Bio. With that logistics. Yeah. Man, it's been Monday. Jeez. That's all right. It won't dampen my enthusiasm. So today, I'm breaking up 7.1. I'm going to do the same thing with 7.2, but I'm going to break it into 2 lessons just because there's a lot in these sections. And today we're going to just focus on sketching what are called slope fields. And a slope field is just a bunch of little short line segments that represent the slopes at those points. And so instead of doing a dot, you do a little line segment that is your estimate of the slope at that point when you plug in that point to the differential equation. So you get kind of a flow going here of a whole family of functions, which will make sense based on our discussions about the fundamental theorems. Right up Jeremiah right in front of me, so you're watching video. You could probably do that today too. This is not a terribly difficult lesson, but it's very new, so you're going to need to see what the new stuff is. So rather than, I don't have the patience for you to write all this stuff down, so you've got a handout that has all this on there, so you can go back and read it and reread it. But an equation like dy dx equals y ln of x, that's called a differential equation because it has a derivative in it. And the derivative doesn't just have to be over here on the left-hand side. It doesn't have to be just treated like an independent variable, but we've got multiple variables in here, y and x. But a differential equation is just that. It's an equation that has a derivative in it. And it could be what we call first order, second order, third order. So there could be second derivatives in there, third derivatives in there, as well as first. This is a pretty simple one with just a single derivative over on the left, on one side of the equation. If you throw in a coordinate here, then you have what's called an initial value problem. And we will be learning some techniques for solving initial value problems and being able to figure out what y was equal to. We'll also learn some estimating methods. One of them we're going to learn tomorrow is called Euler's method for figuring out what the graph of y looks like, even if you can't solve for y. Okay? Because you can't always solve for y. Does that make sense? We've seen that before. So with functions with integrals, you can't always figure out what y is equal to if you have any rule. So that's just talking about what I just said. So it's a bunch of little small slope fields are just graphing a bunch of little small line segments. And when we choose a particular point that it has to go through, that's Euler's method. So then you get a particular solution, not the whole family of solutions. If you think of the slope field as the whole family of solutions to the differential equation, and then the particular solution is that one curve that goes through that particular point. So get your first example in there. Given the function y equals 0.5x squared, write the derivative. So let's write the derivative here. We've got dy dx equals, what's the derivative of that function? Dy dx equals what? X, yes. 2 times 0.5 is 1. Drop the power down by 1. So we got dy dx equals x. So at each grid point, calculate the value of the derivative and draw a short line segment with that slope. So I'll show you what I mean. What's really nice is when we only have a single variable over on the right, you can solve for a whole column of these points. And actually, they typically have one free response devoted to this topic on these weeks. And in my opinion, it's not difficult. Right? So you'll see what I mean in a minute. If I plug in 0 to this differential equation, when x equals 0, I get what? What's my slope? Slope of my tangent line, 0. So everywhere where x is equal to 0, I have a little short line segment with a slope of 0. You with me? So we can take out a whole column here. Remember, we're building a family of functions, of which 0.5x squared is one of them. Yeah. It's kind of cool that, and you can actually download a program in your calculator and do this as well if you want to check it. But you have to be able to do them by hand. Plug in 1 here. When x equals 1, what do I get? Slope of 1, right? So we just have a, and do your best to draw a little line segment with a slope of 1. You don't need to spend too much time on it. We're trying to get kind of a shape or a flow here. And then when x equals 2, you have a little short line segment with a slope of 2. Just 2. A little steeper. And, oh, there should be one there. They're supposed to all look the same through here. And then when x equals 3, we plug in 3 here, and we get a slope of 3. Remember, the derivative is just the slope. And on the calculator, if you do the program, it doesn't take too big of a number before they start looking at vertical lines. But that's what it looks like as we go from left to right. But if I plug in -1 to this differential equation, it's going to be -1 here. So we got a bunch of little short line segments that look like this. And then when I plug in -2, a whole set of slightly steeper slopes, right? -2 would be the slope. And if I plug in -3, and if I plug in -4, I've got this. Start looking almost vertical. And so hopefully you can see it there. You've got a whole family of parabolas. You see them? You could shift parabolas up and down. You could pick a point like 0, -1. If you want to go through 0, -1, there's a parabola that goes through there. Or 0, -2, or 0, 2, or 0, 3. But what we're doing in each case here is we're taking dy dx of different coordinates. Say I put the coordinate in maybe 1, 0. Okay, here is dy dx of 1, that's 1, 1. There's 1, 0 right there, the second one I circled. So if you plug in 1 for x and 0 for y, you get a slope of 1. Y doesn't make any difference in this differential equation. Okay. Here, dy dx of 1, 1 is going to also equal 1. That's the one above it. Okay. So that's what we're doing is it's kind of like going back to Algebra 1 again. Remember in Algebra 1 when you first saw linear or quadratic equations, you made a table and plotted the points. That's what we're doing with these differential equations. We know that a derivative is a slope of a tangent line. So we know that we're just going to plug in an x and a y and then get a little short tangent line that's going to represent that value. Okay. What's the initial condition or an initial condition of the function that's graphed here? What's one point you know that it goes through? For sure. 0, 0. So an initial condition is 0, 0. And then we've got the whole family of y equals x squared. Sketch a function that matches this slope. So it should be on that packet. We're flipping through the packet here. With your notes all in there. Sketch a function that matches this slope field. Just pick one. We can. You might pick a different one than I do. Then try and follow along You just pick any one. We're all picking different ones. Pick a different one than me. We've got that whole family of parabolas. This is a computer generated one. It looks a little better than one I just drew, but it's a little more consistent. And all that's changing is the initial value, or the constant. How is this one going to differ from the first one I showed you, the 0.5x squared? How would this one differ? It's just get steeper, faster. Do you have a guess as to what the function y is equal to that has this as its derivative? This is so the derivative is a linear function, but what would the then integral be if I go backwards? Parabola again, it's actually x squared, yeah, according to the power rule, reversing power rule, yeah. So here we have a bunch of straight line segments here, and you do not need to be too particular about this. You can do this pretty quickly. When you see a differential equation with just an x or just a y in it, see if it's just an x, the columns will match. Just a y, the rows will match. And it's kind of a pain when you have an x and a y, and you got to think about it a little bit more. That's kind of how I think about it. So you're going to practice a couple of each maybe tonight. But yeah, it gets just steeper faster. So I got to make sure this looks like a slope of 2, and then 3 is a little steeper. Not 3, that would actually be 4. And then if I plug in 3, I get 6. I think when you get to a slope of about 6, they just start looking like vertical lines. And if I plug in a -1, I get a slope of -2 here. If I plug in -2, I'll have -4. A little steeper. A little steeper than that. Practically vertical. You get the idea. So field. All right. See if you can sketch this slope field on your own. Go ahead and try it. Plug in some values. Plug in 0. It's undefined. You just don't have anything there. And it's undefined. So at x equals -3 in that whole column, you'll have just nothing written. No little short line segments. Good question. I don't spend a lot of time on this, but I've seen now most years that one part of the free response is just sketching graph lines, and they might have you do actually solve for y, solve the initial value problems. It's a matter of integrating it up, plugging in the initial point, and solving for the constant to get the particular solution. So I'll show you at the end of this lesson what that might look like. That's it. You have any guesses what this function might be? Why? Kind of have to think about parent graph.
-3 would be discontinuity.
At -3, it's undefined, yeah. It's a discontinuity in the differential equation, yeah. What's that? Yeah, I like you're drawing the right function. Think about, okay, there you go. Yeah, because the parent graph is just 1 over x, right? And so what's the integral, what has as its derivative 1 over x? It's ln of x. So this is an ln function. So you're drawing them in the sky. These are totally, because ln it has a vertical asymptote there, right? And then it just grows real slowly as you go to the right. Okay. So, yeah, I knew what you meant. This one I think you'll recognize too. It's a pretty, heavily used function in functional analysis. Sketch the path of the unique solution if the graph passes through 0, 1. So if I tell you it has to pass through 0, 1, what's the unique solution that passes through 0, 1, right? Hey, on here, this is the one. Oh. This is really zoomed in. This only goes up 1, 2, 3. So I think 1 is right here. So what's the unique solution that goes through there? Like that. You recognize that function? 3, 0, 1? No. Let me draw the other one here. This is the. What about path of the solution if it has to pass through 0, negative 1? Here. I briefly got to introduce my Algebra 1 students to these functions because we were studying the rules of exponent. So at the end of that unit, but this is y equals e to the x, or for us e to the x maybe, a to the x for them. That's what you're saying, okay. Something to the x, where x is the variable. Yeah, okay. Right. So this is exponential growth, or that same function flipped over the x-axis, so it'd be negative e to the x. So you can look at the picture of the graph of the differential equation and probably guess as to what the function y equals is. And that's part of the idea today, is being able to look at these differential equations and go, oh, I know what its integral is or what its antiderivative is. So we got it. Y equals e to the x. This is it up here. This is the y equals e to the x, maybe, and y equals, it could be a to the x, I don't know. Oops, negative. Negative. That's just flipped over the x-axis. All right. So given dy dx equals y, now I've switched over to y. dy dx equals y. All those other ones had just an x in it. Y dx equals y. Do you have a slot on your to graph it anywhere? Oh, that's the bottom of 5. Okay. So given dy dx equals y, if I were to graph it, we're going to do this analytically, but if I were to graph it, what they'll do is give you just an array of dots here. Really want to, but let's just do 1, 2 rows. So this time when I'm plugging in values, it's going to be the same horizontally. So like if I plug in 0, I'm going to have a bunch of, plug in 0 for y, so a bunch of horizontal lines right here. And then when I have y equals 1, it's going to be a bunch of lines like that. And then 2, it's going to be like this. So when you're graphing one that just has a y in it, horizontally they're all the same. And it gets even steeper up here. So there's the top half of it. Let's go ahead and think about this. So there's a process called separation of variables. I just want to show that to you with this fairly simple equation, differential equation. What we would do is swap the y and the dx. It would be dy over y equals 1 dx. I'm going to put the 1 in there to remind us that there is there's a constant function on the right, and then 1 over y on the left. And as you guys noticed before, something of the form 1 over x is going to be a logarithmic function. So the process looks like this. It's like what we did with implicit differentiation. Now we're going to do this with integration. We're going to just integrate piece by piece, okay, on each side. And we're going to throw in a constant here because remember that it represents a whole family of functions. So you just integrate each side. The left-hand side, if you integrate dy over y, so you're integrating with respect to y, it's just going to be ln of y. Okay? Because the derivative of ln of y is 1 over y, so this would just be ln of y. And then over here, the integral of 1 dx is just x. And then what we do is we place a plus c in here. We could actually have a plus c on the left and on the right, but if I subtract the c, the constant from the left, over to the right, it just gives me 1 constant. So there's a constant in there. We typically put it on one side of the equation or the other, not both. And then what we want to do here is if we have an initial value, we can plug it in. I don't have an initial value, but if I want to solve this for y, this is going back to last year, what process do I use to solve this for y? What does it happen each side? What's that? I already have logs in here. I got to go the opposite of taking the log of each side. What's the inverse operation of ln of something? Yeah, yes. Yeah, you're on the right track. So yeah, it's e exponentiate each side. And so we can go like this. E to the ln of y equals e to the x plus c. And so in general, here's what we have. This becomes just y. Now I've solved for y. And then here I have e to the x times e to the c. Remember that if the bases are the same, you add the powers. I'm now reversing that process. And e to the c is just another constant. Let's call it a. So we've got y equals e to the x times a, or y equals a e to the x. So in general, when I have a differential equation of the form dy dx equals y, I end up with an equation y equal to some constant times e to the x, a e to the x. So yeah.
Is dy over y 1 over y? Because, like, why is that an ln? Is that because dy is just
Because ln of y has as its derivative 1 over y. So when I integrate it, if I'm integrated it, it's just reversing the process. So it is, it's 1 over y dy. 1 over y
okay,
has as its antiderivative 1 over y. We're going to formalize all that. I'm going to give you a whole list of rules of integration and a whole bunch of, basically they're one, so we'll get there. I handed the list out to you. I think I handed it out to you, but we haven't really talked much about it. All right, so and you can see that happening right here, right? See that exponential function. All right, last one on here, and then I'm going to have you just practice on. Maybe you can finish most of your homework in class. We'll pick some to try. You just need to practice doing these. We haven't done any with just y's. You haven't done any with just y's on your own, or with x's and y's mixed in. Here's the first one. So figure 6 shows the slope field for the differential equation dy dx equals negative 4x over 9y. Look at the slope field. Any guess as to which relation that is that we've studied from the past? Yeah, good. It's an ellipse. Does it make sense that it might be an ellipse with the differential equation of an x over a y? Kind of, right? It involves x and y, and well, so the numbers in front of the x and the y are different. What if they were the same? I mean, what's your guess? What would you infer the shape might be if they're the same? A circle, yeah. So it's like differential equations that are of this form are going to be circles or ellipses. So it says calculate the slope at the point 2, -1. So here's what we do. We go dy dx, and this is the notation of 2, -1. Okay, so it's dy dx, or y prime, It's like f of x notation. It's the same deal. We're just treating these differential functions like functions we've studied in the past. Okay. This is like f of x notation for derivatives. dy dx of 2 negative 1 equals negative 4 times 2 over 9 times negative 1, and so I get 8/9. So if you go over to the slope field over here, the graph of this, and you look over at 2 negative 1, so about 2 negative 1 is right about this guy maybe. Does that look like about a slope of 8/9? A slope of about 1. Yeah, about that. So start at the point 0,2 and draw a graph that represents the particular solution of the differential equation that contains that point. So we go over to 0,2. There it is, right here. And I mean, this is what Matt was seeing. As I kind of follow this around, it's something like that, which is an ellipse. So starting at 0,2. Looks like that's the particular solution. That's a sketch of the particular solution. If you were to find the equation of it, it would be, we got to go back to ellipses. Do you remember the formula of an ellipse? X squared over a squared plus y squared over b squared equals 1. You guys remember? So we could come up with an equation like that to go with this. You know, it might be x squared over 25/16 or something like that, plus y squared over 4 equals 1. That's an estimate. It says solve the differential equation algebraically. Find the unique solution that contains the point 0,2. So let's see if we could solve this with that idea of separation of variables. And I'm officially going to introduce you to this idea of separation of variables a little later on, but it's not difficult. It's just a matter of doing some cross multiplication. What we're trying to do is get the y's together and the x's together. So if I want the y's together and the x's together, it would look like this. 9. Oh, actually, to make this a little easier, let's do it this way. Let's leave the negative 4/9 with the x and move the y over to the dy. So we've got y dy equals negative 4/9 x dx. I think that'll be easier because then y is already, it doesn't have a coefficient in front of it. So it's kind of nice to have y with just a coefficient of 1 to start with. That's kind of a general rule, but we'll talk more about that later. So there's the first step. That's called the separation of variables step. We're getting the y variable over on the side of the dy, and we're getting the dx over on the side of the x. And then we can integrate with respect to those different variables. So it's really kind of similar, to me in my brain at least, to the implicit differentiation that we did last semester. So if I integrate the left side, what do I get when I integrate the left side? I think this should make sense based on what you said. Ellipses are of the form x squared over a squared plus y squared over b squared equals 1. So we better get an x squared and a y squared in the mix here. And we do. This is y squared plus a constant. I'll just leave it y squared. We're going to put the constant over on the right-hand side. And then over here we have, okay, we raise it up 1 power to squared, and then divide by the 2. And divide by the 2. So it's going to be negative 2/9, yeah. X squared, and we're going to put a plus c on there. And it says find the unique solution that contains the point 0,2. We'll see how close I was in my guess as to what it was. But we're going to plug in at this point 0 for x and 2 for y. I think this is pretty intuitive. But like if I want to get c, I wish I had an x and a y to plug in. Well, I do. I have a 0 and a 2. So I plug in my 2 here. Plug in my 0 for x, and what does c equal? 4, just as we expected. And so my equation here, you're going back up to this guy, and you're going to plug 4 in right here. We're just plugging in 4 for c. we've got y squared equals negative 2/9 x squared plus 4. And the only other thing I need to do is move the 2/9 over, so I get 2/9 x squared plus y squared equals 4. And what's the final step to get it in standard form for an ellipse? Divide by 4, divide by 4, divide by 4, divide by 4. So this is y squared over 4 equals 1. I'm putting this off because the fraction is a complex fraction. What does that guy end up equaling? 2 over 36, or 1 over 18, right? X squared over 18. So there it is. There's the particular ellipse. That's the equation of the ellipse in standard form that has the differential equation negative 4x over 9y and passes through the point 0, 2. So we have a lot more techniques to learn for integration before we can do this. This is kind of like full circle what we'll end up with in this unit. It's like the goal of this unit is to find the particular solution to the differential equation. So I'll have to keep reminding you of this as we go through all the different rules that we're going to learn in the next couple weeks here. Is this okay? Okay, let me stop this.